Hello, this is Prithvi Poddar along with Rishabh Dora, and this is our ECS project submission. In this assignment, we were asked to take two RLC circuits and derive the impulse response and the transfer functions along with the filter characteristics. Now I'll be explaining the first filter that we've chosen. This is the circuit diagram for the filter that we've taken. This filter is basically a low pass filter. That means it'll only allow low frequency signals to pass while cutting down the high frequency signals. We'll be proving the filter characteristics in the upcoming part of this video. Here you can see x of t is our input signal and y of t is our output signal. So to derive the LCCD of this filter, we'll first look at the voltage difference between point A and point B. So you can see the voltage difference will be equal to y minus x, and that will be equal to L di by dt, that is the current flowing through the wire AB. In the now by Ohm's law we can say that the voltage difference between B and C, that is y, will be equal to I1R, that is the current passing through the resistance. For the capacitor, we can see that the charge stored in the capacitor will be equal to C into delta V. Delta V is again y for the capacitor. So when you differentiate this equation, you'll get I2 equals to dq by dt, that is C dy by dt. I2 is the current flowing through the wire across the capacitor. Now by applying KCL, we can say that I will be equal to I1 plus I2, and therefore from equation 1, 2, 3 and 4 we derive the final LCCD of this filter. Now, so after deriving the LCCD, when we take the Fourier transform of equation 5, we get this equation, and upon simplifying, what we get is the frequency response for our filter. Upon taking the Laplace transform of the equation 5, we'll get the transfer function of a filter. Now, from the equation 5, we can find the impulse response from the equation 7, that is the transfer function. We can find the impulse response for a filter. So this is our transfer function. We complete the square on the denominator, and then we take this constant term to be k, and we bring it to a form which is something like this, where k is a constant which you already mentioned over here. This is k. So this is our improvised transfer function, and from this, when we apply the inverse Laplace transform on this, we get our impulse response for the filter, which is over here. Now looking at the impulse response, we can find the region of convergence for our transfer function. In the part 1 of the equation, which is this part, we can see that 1 by 2RC plus k plus phi should be greater than 0. So one of the possible region of convergence will be phi greater than minus 1 by 2RC minus k. Part 2 of the equation, which is this over here, we can see that the region of convergence for this part will be phi greater than minus 1 by 2RC plus k. So the final region of convergence for the entire transfer function will be the convergence of 1 and 2, that is the ROC will be phi greater than minus 1 by 2RC plus k. Now we find the poles of the transfer function from equation 8. Since our h of s has a constant numerator, that's why there will be no zeros. The denominator will be 0 at s equals to 1 by 2RC plus k and s equal to 1 by 2RC minus k. So these will basically become the poles of our equation. So in summary, we find that the frequency response, that is h of omega, is this. The impulse response, that is h of t, is this over here, where k square is equal to 1 by 2RC squared minus 1 by LC. And the transfer function is this over here, with the region of convergence to be phi greater than minus 1 by 2RC plus k. Now to check the type of the filter, we take the frequency response. For omega equal to 0, we see that h of 0 will be equal to 1, while for omega tending to infinity, we see that h of omega will tend to 0. Since the frequency response has its maximum at the origin and it dies out to 0 as omega tends to infinity, we can conclude that this is a low pass filter with a characteristic frequency graph like this.
Hello, I am Rishabh Dora, and now I will explain filter 2. So as you can see in this figure, L and C are in parallel, and we are taking the output at B dash node, and we are taking the output at resistor R. So the input we gave is x of t, and the current passing through this thing is I1, inductor is I1, and current passing through capacitor is I2, and the total current is I in the circuit. So applying Ohm's law, we can see V output is equal to IR. So our V output is equal to Y of t. So Y is equal to IR. And by KCL, we can see I is equal to I1 plus I2. And we can now calculate voltage between A and B dash. So our output voltage is Y of t and our input voltage is X of t. So voltage between A and B dash is Y minus X. And now by applying simple formula delta V equal to L di by dt, we get this formula Y minus X equal to L di1 by dt. And we know this, that Q equal to CV. So here our V is equal to V minus X. So we get this formula Q equal to C Y minus X. And we want now I2. So we differentiate this equation and we get I2 equal to C d delta V by dt, that is C dy minus X by dt. Now using 1, 2 and 3 in this equation, we get Y equal to I1 plus I2R, and now we simplify this equation and we get this equation. And so this is basically our LCCD for this filter. Now we will take Fourier transform of this equation and Laplace transform of this equation to get frequency response and transfer function. So first, taking Fourier transform of equation 4, we get this equation, and now we know that Y by X equal to H of j omega. So we simplify this equation and we get this equation, and this is our frequency response. And now we will check the type of filter by our frequency response. So first we check it at omega equal to 0, and when we put omega equal to 0, we get h of 0 as 1, and when omega is tending to infinity, we take limiting value of it and we get that value also equal to 1. So now we can see that our numerator will get 0 somewhere in between. So if we put our numerator equal to 0, we get at omega equal to plus minus under root 1 by LC, our h of j omega will become equal to 0. So by seeing this characteristics, that is at origin it is equal to 1, and at plus minus infinity it is equal to 1, and at plus minus 1 by under root LC it is equal to 0. So we see that this is actually a band stop filter. And now we will take Laplace transform of our equation 4 to get transfer function. So taking Laplace transform of this equation, we get this equation, and we know that Y by X equal to H of S. So simplifying this equation, we get our transfer function, which is equation 7. Now we have to find it zeros and poles, and also its region of convergence. So we will further simplify this equation. So we have taken R common from this equation, and we have put LC equal to alpha and L by R equal to beta. and we have added +1 and -1, and we have simplified this equation, our transfer function, as this. Now we will use completing the square in the denominator to further simplify this equation, and after doing that we can also put our denominator equal to 0 so that we can find the poles of this equation. So we found out our poles p1 comma p2 equal to beta plus minus under root beta square minus 4 alpha by 2 alpha. Now we will use partial fractions in this, and we can write our h of s equal to this equation. Now if we take the inverse Laplace transform of this equation, we can find our h of t, which is impulse response. So we take Laplace transform of this equation and we get our h of t as this equation. Here p1 and p2 denotes the poles, and alpha and beta denote LC and L by R respectively. And if we now we will find our region of convergence. Now for region of convergence, this part should be greater than 0 and this part also should be greater than 0. So we will take this intersection and we will get our region of convergence. And this was our filter 2. So thank you so much. This was our ECS 204 assignment.